Hello, welcome to this last video in this series on Lagrange Multiplier method. We've done 2 examples. Here's now the 3rd example. And at the end of this video, I'm going to go back and show you some alternative methods if you don't want to follow the suggested algorithm or recipe. All right, so in this example, we have, it's a classic kind of example. You don't have to use Lagrange Multiplier method for it, but I want you to know that once we ramp it up and go with more variables, this would be the best method to solve it. So we're looking for the point that's on the circle with a strange radius that is closest to some point that's not on the circle, of course, 1, 2. Here's the visual. Circle of radius, what is that, 3 root 5? Yeah, circle of radius 3 root 5. And this point is inside the circle, 1, 2. Now, when you're trying to say closest, that word closest indicates to you that there's a distance that you want to minimize. Okay? That point is 1, 2. Any point that's on that circle, generically call it x, y, and we can get the distance from a point on that circle to your point 1, 2. But generally, the distance formula has this square root on it, which makes taking derivatives quite difficult. So instead, the way the square root function grows, it's monotonic. When you put something larger in, you'll get something larger out. And so instead of minimizing the distance, we can minimize what's underneath the square root and thereby still minimize the distance. Okay. So we'll minimize the square root of this function. Minimizing the square root of f will minimize f. Oh, that's bad. That's bad wording there. Minimizing the square root of d. That looks weird. Minimizing f will minimize the square root of f. I don't know, it's really weird the way it looks. Sorry about that. I feel like that should be the other way around. I know it's triple equals means equivalent to. But anyway, minimizing this function will be same thing as minimizing. We'll be minimizing the square root of this function, which happens to be the distance. This is the distance here. All right, great. Because we have x minus 1 quantity squared and y minus 2 quantity squared added up. When you take the square root, you'll have the distance. Okay, so what are we doing? Lagrange. Okay, so what's the constraint? If this is the function we're trying to minimize, what is our constraint? Similar to the previous question we had, the constraint is that you have to be on the circle. So x squared plus y squared must be equal to 45. But when you write the constraint, remember to set it equal to 0, so we'll move the 45 over to the other side. Just a suggestion. You don't have to do it. What do we do then? Just a suggestion. We're going to create this capital F function based off the lowercase f and the g. Little f minus lambda g will be capital F. Why do we do that? So that we can take the gradient of capital F and be able to see all the equations right after, one after another, and then be able to make our way through it, hopefully in a better way, in an organized way. And so the capital F function is little f minus lambda g. The gradient of f is based off of partials. What is the x partial? 2 times the quantity of x minus 1, as far as the lambda goes, minus 2x lambda. What is the y partial? 2 times the quantity y minus 2, minus 2y lambda. Officially, the lambda partial is going to be minus g. It always is set up this way. And we'll set these all equal to 0. And in doing it, we'll try to set, have the, so let's go ahead and distribute maybe. Yeah, let's go ahead and distribute. Or cancel out the 2's if you want. And that way we wouldn't have to distribute. When we set this equal to 0, the animation's off, sorry about that. But it will have, we can cancel out the 2's. We can say divide both sides by 2, and we'll end up with x minus 1 minus lambda x equals 0. Y minus 2 minus lambda y equals 0. And then the lambda partial means that you're on the circle. All right, great. So now we have the ability to factor out, maybe. We have the x's, 2 terms with an x on it, so factor out the x. 2 terms with a y on it, so factor out the y. And hopefully you see a pattern. You don't have to see a pattern, but if you're doing this and you see a pattern, please exploit that pattern. You can abandon the technique. The technique is just guidelines, okay? But if you see a pattern, exploit that pattern. What I see is that when I go to, normally this is not the way to do it. Normally we solve for lambda, and then we work our way through that minefield. But I see that x is 1 over 1 minus lambda, and y is 2 over 1 minus lambda. That stands out to me. I see it. It's one of those see it or not things. That's how shortcuts work. When you see them, you exploit them. When you don't, you got to grind out the regular way. I'll show you the grind out the regular way on the next slide. But here we have it. What is it that we have? What are we trying to get? As we're doing this, our goal is to get y as a function of x or x as a function of y. And sometimes it's all intertangled, but this one is actually untangled. There's no entanglement here. You see, when I look at these two equations, I see that y is twice x. And so I have what I need. Why bother jigging through all this mess? If you see it, use it. Okay? That's what you need. Well, what do you do with that? Once you have the relationship between y and x, you take that into the constraint. Replace the y with twice the x. And you'll have 5x squared equals 45. So that's nice because x squared equals 3. I'm sorry, x squared equals 9. So x is plus or minus 3. And if y is double x, then you're going to be the point 3,6 and the point -3, -6. These points are on the line. And so that line is the line y equals 2x. One of these will give a maximum distance, the one that's further away, and one will give a minimum distance, the one that's closer. Now, what we'll be getting will be the function f, which is not really the distance. We'll get 20 if we plug in 3,6. We'll get, I think it's 80. If we plug in -3, -6. That's not the distance, okay? But it will lead to a distance of 2 rad 5 for the close one and 4 rad 5 for the furthest away one. So the point on the circle that's closest to that point would be the point 3,6. And the distance will be 2√5. You solved it. And you were able to make it through with minimal work because you saw a shortcut. Somehow there was a pattern and you exploited that pattern. I can't make that part of my algorithm, part of my recipe, like seeing patterns or not. If you see them, use them, think of them as like a shortcut and go with it. Okay? This same question without seeing the pattern looks like this. Solve for lambda, set them equal. Worry just a second about dividing by 0. Do some cross multiplying, get the same relationship that y is twice x, get the same result of 3 and 6 and -3 and 6, get the same answer in the end. It works. It's a standard way. I can't say it always works, but it's a standard kind of a approach to a Lagrange multiplier question. What did? We saved ourselves some work of grinding through lambda equals, and okay, we saved that little bit of work. Maybe that work ends up being 4 minutes of time, which is going to be critical on these problems. Okay, what I skipped over was I told you that we could have done the example 1 another way without following the recipe, following the algorithm. And so, the driving equation is that the gradient of f is lambda times the gradient of g. That's the driving equation behind Lagrange. And so you could just go there. You don't have to do capital F and all that. If you don't feel like you want to do that, then go right ahead. It's fine. What I'm providing is structure. And if you don't need that structure, go with it. Take your gradient of f. Take your gradient of g. Set them equal component-wise, and you have your equations. It's a little bit more messy, but you'll get there. Algebraically, it's you got to be really sound to make it through using this method. Okay, but it works. It gets you to the same point. Okay, in the end. All right. Thank you for watching this video. My name is Nakia Rimmer. Please comment down below, like and subscribe. Reach out to me if you need any help. Go to my website if you need extra resources. I'll see you in the next video.